red-tipped match is coated in red phosphorus, but this is not phosphorus in its pure form. Phosphorus in its pure form looks more like this. But if this were actually real phosphorus, it would spontaneously explode in air right now and blow up into the biggest bright light you can imagine. So how and where do we discover something like this that burns in air, and explodes, and burns skin on contact? Well, I'm going to tell you where in history, where it is in the world today, and where it is in your bodies.
Is it a PowerPoint you're trying to move?
I'll do this enter. About 300 years ago, a German guy peed in a cup and boiled its contents down, creating a highly flammable substance. He was actually trying to create gold, but he found phosphorus. 100 years later, Boyle boiled his pee down and made a more concentrated form of phosphorus. He made matches. Then about 100 years later, we found out that phosphorus is actually in our bones. 85% of our phosphorus in our bodies is in our bones. And Lavoisier made phosphorus part of the periodic table. Then we found out that phosphorus is in rock. Most of the phosphorus is in rock that's by the ocean side or by streams. It's got appearances. White is what you saw in the pure form, except it would have exploded. Red is made from white, and black is also made from white. There's some pictures here. We put a burn ban on white phosphorus, the Geneva, I believe, after World War II. It was causing too many problems. And we don't like it burning up on our matches because if you inhale even 1/10 of a gram, it's fatal to our bodies. And phosphorus is currently used in many parts of the world today. It's obviously in our matches, it's in our urine, it's in the rocks. We've got it in fireworks, explosives and warfare. We used to put it in detergents because it kind of made it bubbly, we thought it clean, but we don't do that so much anymore. But it is in fertilizer, the soda you're drinking. It's in Jolly Ranchers. It's in your science laboratory. We mine about 153 million tons a year, so there could be a problem with us running out someday. And we also use it in manufacturing plants. If you go in your refrigerator and you see baking soda, that's not phosphorus, but it's made from phosphorus plant. So where is it in our bodies? Like I said, 85% of it is in our bodies. And in order for you to understand how it plays a role in bones, I'm going to have to explain a little bit about the bone structure. And I'll use this room as an analogy. So this room is what we're going to form into a bone, and we got to have some workers to build the walls up. So we'll consider ourselves the workers. So we go outside and we get the materials to build the walls. We're a bunch of carpenters to build the walls up. So we go out and we get some lumber, a bunch of 2x4s. We bring them back in here. We stack them up. We've got our walls built, and we're looking good. But there's nothing really holding the 2x4s together. So what happens when you push on the walls if there's nothing holding the 2x4s together? Falls down. So what do we put in 2x4s to stick 2x4s together? Nails. So we're good carpenters, so we go back out and we get our nails and we come back in. And these nails got a nice pointy end with a good head on it. That pointy part is your calcium and the head's phosphate. We're talking about phosphate here. That tacks those 2x4s up, and then we got our bone structure. And if you know anything about bones, the little carpenters were called osteoblasts. And what we do is we go out and get the 2x4s, those are our collagen fibers, and calcium phosphate are the nails. We've also seen phospholipids, so not only does phosphorus weld our bones together, but it also welds together our phospholipids. We've all seen this, the glycerol with 2 fatty acids and a phosphate. The phosphate gives the glycerol head a charge, which makes for a hydrophobic material, keeps the membrane, all the lipids out of the membranes. It also welds together our DNA. We're pretty familiar with the structure of a DNA. This is our deoxyribonucleic acid. Just like the word means, we have our nitrogen base in the middle, adenine, thymine, guanine, cytosine, etc. And then here we have our pentose sugar, ribose, which has a carbon ring. The phosphate that we're talking about hooks onto the 3rd and 5th carbon on that ring, and it welds our DNA together as well. And not only does it play a role in welding our body together, but it is part of energy. ATP is energy. It's our body's currency for energy. And I'm not going to beat a dead horse on this issue. We've all seen that this is what ATP is. We've got the 3 phosphorus, but it's in a phosphate. Phosphorus, if you pull off the P off the periodic table, it doesn't just float off and go out in nature. It's highly reactive. So in our bodies, 4 oxygens automatically attached to it. Anywhere phosphorus is in the body, it's phosphate. So here we have energy, and we all know how glycolysis works. You've got your glucose molecule, and we invest a couple of these phosphates on the sides. It breaks down, it goes through the acetyl coenzyme A and the Krebs cycle. And it's basically what this whole energy production is. It's kind of like shooting hoops. We've got these hydrogens that we're kicking off of these molecules the whole time. And these hydrogens are being shot over into these baskets. And this is on in the mitochondria, there's the cristae, that's that folded interior, and that's where all this is happening. So we're shooting these hydrogens through these hoops, and every time we shoot it through, some energy is released. Energy goes down our ETC here, and so what we have is we got all these hydrogens up here. It's very acidic, and all the no hydrogens down here, so it's very basic. So the hydrogens, we have a proton gradient. So the hydrogens want to get down in there as fast as they can. So what they do is the biggest hole is over here, the blender. That's what I call it. It's the ATP synthase. We've got the hydrogens, and what they do is they're so full of energy because they're so full of a proton gradient that they kick down there so fast it churns this blender. At the bottom of the blender, somehow, we've got these ADPs, that there's 2 of them, they're missing 1. They're floating around there with this phosphate loose. Somehow in that churn, it smashed it together and we get energy. There's a lot of other roles that phosphorus plays in our body as phosphate, but I'm not going to go through all of them. It affects our nervous tissue, fluids, and electrolytes. It's in our CNS, our muscle contractions. And the kidneys is basically what's going to filter out. There's a picture of the kidneys there. You can't really get too much phosphorus. It's almost in everything, and the kidneys kick it right back out. We know there's 20 amino acids. 9 of those are essential. Well, there's 25 minerals. 16 of those are essential. This is why this is essential, because the kidneys, we urinate right out. So we got to keep consuming it. You could get a deficiency in it. Normally not in our country. We have enough food. We have enough chicken and beans and rice. It's in your soda. It's in all the foods we have. And we have a lot of that here. But in other countries, they might have deficiencies because of the lack of foods. And if you don't have enough of the phosphorus, everything we went through, you're lacking. So the energy, well, you're feeling less energetic. The bones, your bones are more brittle and weak. In fact, in developing with a lot of children, if they're missing phosphorus, which coincides with calcium, that nail, what happens is they keep growing. Their growth hormones probably still kick in. So they're growing, but they're not hardening their bones. So what happens is the bone elongates and becomes weak, and it will start to bow. Later in life, after they consume enough calcium phosphates and it starts to harden slowly, they've got these bones that were already weak, so they had bent and they form bowed legs and whatnot, and that's called rickets. So there can be deficiency in phosphorus that coincides with calcium as well. And here's a picture of rickets, the bowed legs. They don't look that comfortable. Consuming phosphorus, it's in all, we talked about this, salmon, turkey, chicken, eggs. The FDA says you can eat about 1,000 milligrams a day. We get almost double that. The U.S. RDA says 800 to 1,200. If you got a little baby, that you're talking about 100, of course. More than 6 months, maybe a couple hundred. I'm a pretty fit guy, so I take in the 800. So who do you think takes in the 1,200? Well, it's not our Olympic swimmer necessarily. These are teenagers. Teenagers are going through their growth spurts, so they're the ones who need